Hi everyone, I will start by introducing our data collection process, including how we sample the images and the overall data distribution. We collected walkway-focused campus images on Penn's campus and used GPS metadata from the photos as labels. In total, we collected about 4,500 images. 3 team members collected in parallel along the main walkways using different step intervals, 5, 10, and 15 steps to reduce sampling regularity while maintaining coverage. At each sampling point, we rotated in place and captured 6 to 8 overlapping views, so each GPS point has multiple directions and compositions. We kept camera height consistent and included slight up tilt and down tilt. This map shows dense GPS trails following the walkway network in target area, indicating continuous sampling along paths rather than clustering at a few locations. Here is the distribution across 5 collection sessions. Splitting collection into multiple sessions helps capture day-to-day appearance changes. This histogram is daytime heavy, but covers morning, noon, and afternoon, which helps generalize across different lighting and shadow conditions. Finally, we included challenging cases, blacklistings, occlusions, rainy weather, and dusk to reflect real-world variability and improve robustness.
After completing our initial data collection, we performed an additional quality control pass to ensure that every image in the dataset was truly informative about model training. The main goal here was to remove frames that would act as noise. Specifically, we filtered out several categories of low-quality data. This included images with large area occlusions, such as a parked car or a passerby blocking most of the walkway, severe motion blur caused by camera shake, and views dominated by non-informative content, like shots facing mostly the ground or captured at an extreme tilt. Removing this helped us improve label-to-visual consistency and kept the dataset focused on learnable landmarks that actually help the model localize. To make this process reliable, we manually review the dataset after extracting and verifying GPS information from the image's EXIF metadata. This ensures that only visually informative view-aligned samples were retained for training. Overall, this quality control step helped remove noisy samples and ensure that the remaining images provide clear and meaningful visual signals for model training. This slide shows our data pre-processing and augmentation pipeline. Because the dataset contains images captured in different orientations, we first reset each image while preserving its aspect ratio. The longer set is scaled to 1792 pixels, and the shorter set is padded with zeros to obtain a square 1792 by 1792 input. This padding does not affect learning, as the model places little attention on padded regions. We then apply data augmentation to improve robustness, including random rotations, color jitter to simulate changes in lighting and camera settings, and Gaussian blur to model minor camera shake. These augmentations help the model generalize to real-world variations encountered at inference time. All of these pre-processing and augmentation steps are implemented directly in the dataset class and applied on the fly during training. Finally, the images are normalized and split into 64 non-overlapping 224 by 224 patches, which are fed into the model.
So our model is generally inspired by the design philosophy of vision transformers, VIT. However, we'll make a modification. The original VIT paper points out that to outperform CNN-based architectures, a transformer model typically requires a very large amount of pre-training data on the order of 100 million images to surpass the networks such as ResNet. However, our dataset contains only is far from sufficient to train a pure transformer effectively. To compensate for this limitation, we introduce visual inductive biases by incorporating a CNN architecture. Specifically, the CNN backbone provides periods such as locality and translation equivariance, allowing it to extract the details from each patch and effectively encode local visual information. The attention enables the model to capture global context without being constrained by limited receptive fields of CNNs. Through attention-based interactions between tokens, the model can dynamically focus on more important patches where scene variations are significant. We use MSE as the training loss because it is simple and easy to optimize. To mitigate overfitting, we additionally introduce the L2 regulation term. MSE is also used as one of our evaluation metrics. In addition, we use RMSE to evaluate model performance as it is more intuitive to interpret compared to MSE, while showing the same overall trends. When selecting models, we jointly consider the validation RMSE and the test RMSE on the 100 official images. Only when both metrics are relatively low, indicating strong accuracy and generalization, do we choose the model as our final submission to the leaderboard. So the table presents our evaluation of different CNN backbones and their comparison with the baseline. When using ResNet 18 as a backbone, we observe a substantial improvement over the baseline, demonstrating the effectiveness of incorporating the attention mechanism. In contrast, ResNet 50 performed worse than ResNet 34, which may be attributed to its large number of parameters, leading to overfitting as well as its longer inference time. The efficient night model yields inferior results due to architectural constraints that limit the batch size, resulting in the unstable batch normalization statistics. Based on those observations, we ultimately select ResNet 34 as the CNN backbone for our final model. So beyond the CNN backbone, we explore the additional modifications by introducing a global visual token to complement patch level features. However, this change unexpectedly increased the IIC. Attention validation reveals three reasons. First, the global token dilutes the attention of the prediction feature token, leading to more dispersed attention as shown in Figure A. Second, it competes with the prediction feature token for global information aggregation, resulting in weak attention highlights in Figure C and Figure A. Third, the global token introduces unfavorable inductive biases from CNN backbone, causing the model to focus on incorrect regions, such as the incorrect wall in the Figure C. So you can see that in the attention distributions. To better analyze our model, we developed a new attention visualization method tailored for the visual tasks. The method is based on attention rollout, but with significant optimizations. We extract attention metrics from each multi-head attention block, recursively propagate them to obtain a global attention distribution, and then project the result back to the original image for the visualization. And you can see that for the good model, the attention distribution is very well. The model can pay attention on buildings, the very special case in this thing. But for the bad model, the model may pay attention not only on the buildings, that is very important to recognize the position, but also pay attention on the trees that is irrelevant to the current thing. And that's all. Thank you.